For this first question, we need to combine the powers of 2 in this thing with the powers of 5 to get something that will end in a lot of zeros. Here is the full calculation if you want to pause the video and read it. But eventually we just get 2 to the power of 10 times by 10 to the power of 30. This 2 to the power of 10 is 1024, which has 4 digits. This 10 to the power of 30 is 30 zeros at the end of it, so that is a total of 34 digits. For this question, to get rid of the square root, I need to square both sides, which gives us this over here, and after simplifying this we get that, and the 2 plus the 3 add up to the x, so we get that x must be 5. For this question, the area of a semicircle is just half the area of a circle, so it's pi r squared divided by 2. So therefore the area of this semicircle is just pi over 2. Same with this one. Same with this one over here. Then we've got the area of the circle, the bigger circle, that is pi times by 2 squared divided by 2, which just becomes 2 pi. Now I can subtract these 3 from that to get the area of these 3 pieces. That will be 2 pi minus 3 over 2 pi, which is pi over 2. However, the question only asks for this shaded region and that shaded region, so I have to also subtract the area of this region. And to work out the area of that region, let's just draw another diagram. We can just, to work out this area, we can work out the area of this rectangle and subtract the area of this semicircle over here. This rectangle has side 2, 1, so it's going to be 2 minus the area of the semicircle, which is pi over 2. And so in the final step, just have to take this and subtract that, and we'll get pi minus 2, which is this one. Okay, for this next question, when I saw it, I thought of binary. Basically, binary says that there's only one way to express a number as the sum of different powers of 2. For example, the number 100 is equal to 2 to the power of 6 plus 2 to the power of 5 plus 2 to the power of 2. Now, in binary, you'll usually just represent this as 1, 1, 0, 0, 1, 0, 0. So, but we don't really have to represent it in this form over here. So what I did was I took this number 10 and I expressed it in binary, and we get 10 is just 2 to the power of 3 plus 2. Then I replace 10 with this because it's equal to that, and we get 2 to the power of 3 plus 2 times 2 to the power of n equals 2 to the power of n plus 2 to the power of n plus 2. This side over here becomes 2 to the power of n plus 3 plus 2 to the power of n plus 1 equals 2 to the power of n plus 2 to the power of n plus 2. And the only way that these two sides can be equal is if this is equal to that and this is equal to that. So n is equal to n plus 1. So it asks for the difference, and so the difference between them is just 1. Looking at this question the second time, there is another way to solve it. I can take out the factor of 2 from this, and we get 5 times by 2 to the power of n plus 1. And here I can take out the factor of 2 to the power of n, and we get 2 to the power of n times by 1 plus 4. This 5 cancels with that, and we get that 2 to the power of n is that. Okay, now for this problem, for this to be a real number, the value underneath the square root must be positive. So we must have that n minus n squared plus 15 must be greater or equal to 0. Now, it's possible to factorize this and find out for what range of values of n are there that this is positive, and they teach you this method in school. However, for me, it just felt like it'll be faster just to try different values of n. We know that this over here is a parabola, and we know that there are 2 intercepts for when it becomes negative, and between these 2 intercepts it stays positive. So I just tried different values of n until I find the integers where it crosses over. For the input of 3, we get 2 minus 2 times 9 plus 15, which is 0. For the input of minus 3, we get minus 3 minus 2 times 9 plus 15, which is definitely less than 0. For the input of minus 2, we get minus 2 squared plus 15. This over here is going to be minus 10, which is greater than 0. And so it crosses 0 somewhere over here on the negative side, and crosses 0 here. And now I'll just have to count up how many integers there are, and it's probably faster just to 6. You can also do this using the high school method. I'm going to go on about a 4-minute tangent on how to explain that, but you can skip that if you're familiar with it. Let's just rearrange the terms so that it looks like a normal quadratic. Then I need to factorize this, which factorizes like this. Then I'm going to factor out this minus 2 so it gets in a more familiar form. And what we do here is we consider the cases when n is larger than this largest intercept, when n is between these 2 intercepts, and when n is smaller than this intercept. So we've got the case when n is larger than 3. We've got the case when 3 is greater than n is greater than minus 5 over 2. And we've got the case when n is smaller than minus 5 over 2. At the cases when n is 3, then this whole thing will just be 0. Now, when n is greater than 3, we can create a table for what's going to be the sign of all of these parts of these terms. Okay, I'm a little bit rusty because it's been a long time since I've done this. What's going to be the sign of all these terms? When n is greater than 3, this one will be positive. This one will also be positive because we have 3 plus something. And this one will always be negative. When n is smaller than 3, this one becomes negative. But if n is still greater than this, this will remain positive and this will remain negative. When n is smaller than minus 5 over 3, this term will still be negative. It basically changes from negative to positive at this point and never changes again. This one changes from positive to negative, and this one remains negative. And the net effect when we multiply all these together is when n is smaller than minus 5 over 3, the product is negative. When it's between these numbers, the product is positive. And when it's greater than 3, the product is negative. If you're familiar with these problems, you'll realize this whole thing changes sign. Every single time one of these change sign, and it's easy to see when they change sign, basically at minus 5 over 2 and 3. And then all you have to do is work out what's the original sign it had when it's smaller than minus 5 over 2. Change the sign once at minus 5 over 2 and change the sign again at n is 3. By the way, if one of these terms are squared, then this thing will not change signs over there, and that's just something you must keep in mind.